Okay, so let's start now. Okay, so we'll continue with sequential circuit. So last time around we saw circuits that try to remember some of the history, which is what you're calling a state. And we also saw the flip-flop, the D flip-flop, which is a circuit element that stores the state, and every time a clock edge, a rising clock edge comes, typically then it copies whatever is present on the input and kind of stores it, and until the next clock edge, the output of the D flip-flop is whatever it captured in the previous clock edge. And we've also seen SR latches and all, but typically we don't use them in the design, so D flip-flop is kind of the main element. So today what we're going to do is to look at some more complicated circuits using these flip-flops, and then also go into how we design the sequential circuits in a more complicated sequential circuits using something called finite state machines or state diagrams. The TAs started on them a little bit during the last discussion section, but we'll sort of look at them in more depth today. So let's look at the circuit where what we have is D flip-flop, an n-bit D flip-flop, which is nothing but n 1-bit D flip-flops with all their clocks tied together, and the n bits of our data bus feeding into the different D flip-flops, and then the output again n-bit, and in this it feeds back, and at the input what we have is an adder, an n-bit adder. One of the inputs is nothing but the output of this flip-flop, and the other input is 1. So specifically, it's 0, 0, 0, 0, n minus 1 zeros followed by a 1. And so if you look at this, then at any given point in time, the output of the adder is whatever the flip-flop has at its output plus 1. So at this stage, so if I were to look at this wire at any given point in time, it's going to be count plus 1, and or specifically count plus 1 modulo 2 to the power n, because we have an n-bit adder. So every time then a clock tick comes, then the flip-flop stores the new value in the flip-flop is going to be count plus 1. So if I look at the output of the flip-flop, then at every clock edge, it is going to increment. So if we start out with 0, after the first clock tick, it will become 1, 2, 3, all the way up to 2 to the power n minus 1, and then it will roll back to 0, and that process will keep repeating. So in this particular case, the state, which is the content of the flip-flop, is giving us what? What would the state represent in plain English? So again, remember we had said previously, state is a relevant part of the history. So what is the state telling us now? Anyone? So it's counting, right? Every clock tick it's counting. So after 10 clock cycles, after 10 clock edges, what would be the content of the flip-flop? Let's say we started with 0. Well, it will be 10, right? A binary representation of 10. So after n clock cycles, or whatever, some k clock cycles, the content of the flip-flop would be k. So what is the state in plain English? It's the number of clock cycles that have passed since the system started, right? So in this particular system, the state, namely the n bits of n bits stored in those flip-flops, is basically telling us how many clock cycles have passed since we started. So the state of a system is nothing but the information stored in the memory, because that's all that we remember about the past, and that tells. So when I said earlier on that is the relevant part of the history, then in this particular case, it's basically the relevant part of the history corresponds to how many clock cycles have passed since we started, or again, more precisely, number of clock cycles that have passed modulo 2 to the power n, because we have an n-bit flip-flop. So if I were, if we had started with, let's say, the initial clock edge was 0, 1, 0, if that's how it started, then it will count as 0, 1, 1, 1, 0, 0, and so on and so forth. So things also depend upon if the flip-flop were not initialized with 0, 0, 0, then the state would correspond to starting value plus number of clock cycles that have passed modulo. So for a complete description of a sequential system, you also therefore need to know what you started out in, what were the initial contents of the memory, because at every clock edge, the new content of the memory depends upon the input to the system as well as the current content of the memory, and that's how we are updating. That's our next state logic that we had seen last time around. So in this particular case, what is the next state logic? Adder, right? So the next state logic is the adder. It's taking the current state, which is count, it's taking the input, which is 0, 0, 0, 0, 1, and it's generating the next state, which is count plus 1. What about the output logic? Output logic is basically output is equal to current state, right? If that's what we are outputting. So typically, when nothing is shown out here, then typically this means that this is my output. So output function in this case is dependent only on the current state, and it's equal to the current state. So in this particular, so counter certainly is as you can imagine, is a useful thing, because there are a lot of examples like, I don't know, simple circuits that count number of cars going past the turnstile or things like that. So counter is a useful function, but this notion of state and then having doing some operations on it is useful for a wide variety of things. Again, in the discussion section, the TAs went over an example where they were doing pattern matching. So the idea there was some string of symbols coming in. There could be data from a sensor, and we are looking for some pattern in it. So in that particular example, those of you recall, there were letters A, B, C, D. I think there were 4 types of letters coming in. So each time instant, you were getting a character, which could be A, B, C, D. And the problem was that we wanted to look for a particular pattern, which was A, B, C, A. Okay, so what we needed to remember was what were the 3 previous characters we have seen. Because if we just look at the current character, that's not enough to do the pattern recognition. So we had to remember something about the preceding 3 characters. So in general, given a problem, the output would require some knowledge of the history, and the art of designing sequential systems boils down to that what is the history, what is the information from the past that you need to remember, because in the worst case you can say, hey, I need to remember everything about the past, okay, but that can result in infinite state and is usually not required. So given the problem specification, you have to kind of figure out what's the minimum state that I can get away with. So state, you can say that there's a set of states, distinct states that I need to remember, and then log 2 of the number of elements of that state is the minimum number of bits you need to represent the state. But we'll also see how the state could be represented many Just a simple example, a counter which is basically telling us how many clock cycles since the start, or how many clock cycles plus the starting value. Now, there are when it comes to sequential circuits, there are several different types of problems that you would encounter. One is, I'll give you a complicated description, like we have seen in the homeworks, thermostat example, the midterm, we had In those cases, the system was doing a pure function. In other cases, I might ask you to do something which will require you to design a system where the system needs to remember something about the past. So those are problems of design. Then you also have problems which go in the reverse direction. Given something, you have to kind of figure out what is it doing. So you might be given a circuit where there is some combinational logic, some flip-flops, and you have to kind of figure out what is it that it is doing. That's the analysis kind of thing. So given any digital circuit, you can always kind of lump up all the flip-flops in one place and lump up all the combinational logic in one place. So any arbitrary digital logic, if you draw it appropriately, it will look like this. It will have some combinational logic. Combinational logic is going to take input from the outside world. The combinational logic will take the current state, which is the output of all the flip-flops, and then it's going to produce the next state for the flip-flops, and it's also going to produce the output, which is going to the external world. So any digital system can be redrawn to look like this. Okay, in some cases, parts of this combinational logic function may be trivially simple, like we saw previously in the counter example, where the output was the same as current state. But generally it would look something like this. And then by looking at this, looking at the combinational logic, you can then write down what the system does in terms of what is this kind of a state table. So this is the counterpart of truth table in case of combinational logic. In state table, not only do we have inputs and outputs, but part of the input also, we also need to consider what is the state, current state, or simply state, and then what is the next state. So there are these two additional columns. So in a combinational logic, we only have the inputs and the outputs. Now we also have state and the next state, or current state and the next state. So let's say if I were to give you something like this, where I say, okay, so 1 bit of input, 2 bits of state, 1 bit of output, and of course 2 bit of next state. So firstly, how many distinct possible states the system can be in? No, how many state bits are there? 2. So it could be in 4 states, right? So the number of states possible in the system is the number of flip-flops it has. Now, not all those states may be reachable. What I mean by that is you power up the system, you let it run, and it may be that it will never reach some of those states. But that's the max 2 to the power n, where n is the number of flip-flops, is the maximum number of states possible in the system. So another way of saying is that there are only 2 to the power n relevant histories that we care about, right? Each state represents a different history. So in this particular case, we have 4 possible state values, and then this combinational logic, in a sense, is a mapping from in and current state to the out and the next state. Okay, so and the sum table out here. So what you what you see is what this combinational logic is kind of doing. Now, let's see what happens. So best thing when faced with something like this, and combinational logic itself, you would be given, it would be perhaps some sort of gates and all. So you can always, given this combinational logic, you can always come up with this table. But then what? I mean, now you have to kind of figure out what is it doing. Sometimes it may be some very obvious function, sometimes not so. So let's see this particular one. What does it do? And so mentally, what you need to do is to kind of simulate the system, run the system. At every clock edge, what happens? We kind of did it last time for a couple of examples, which were very abstract. So this one is a more concrete example. Now, the very first question would be, at t equal to 0, what are the contents of the state register? That needs to be given to you. So in this particular case, we are given that the state starting out with is 0, 0. If the state starting out was different, then the system would behave differently after t equal to 0. So this is something that you have to be given. So state is given as 0, 0. Input is 0, so at the clock edge. And so 0, 0, 0, the output is 0. Now, what would be the next state after this? So when the next clock tick comes, what do you think would the state of the system becomes. So current state is 0, 0, input is 0. Looking at this, input 0, current state 0, 0. So the next state would, so clock cycle 1, next state becomes 0, 0. But the input which is coming from the outside may change. So let's say in this particular case, I'm given that the input has changed to 1. So when the next clock tick comes, the system goes from state 0, 0 again to state 0, 0. It stays there because that's what our table says. Our table says that if input is 0 and current state is 0, 0, then next state is 0, 0 and output is 0. So that we see. So output is given us to be 0 here, and this is the next state part. So that follows from this row. Okay, but now let's say at that clock edge, input has changed to 1. So what would you think would the next state be? When the next clock tick comes, what would happen to the system? So 0, 1. Okay, so let's see. Yeah. So input is 1. Current state is 0, 0. Next state would become 0, 1. So next state becomes 0, 1, and again input, let's say, stays at 1 in this case. So in something like this, you also have to be given how the input is changing because that's being changed by the outside world. Okay. So and output, well, if input is 1 and current state is 0, 1, then the output is 0. So we kind of see that output to be 0, and that whole process kind of repeats. I'm not so after this now current state is 0, 1 and input is 1, so 1, 0, 1. Next state is going to be 1, 1, and that's what we see as a 1, 1 out here, and this process will keep repeating. So I'm not going to walk through all of that. So given a system, looking at its combinational logic, you can come up with the state table, and then given that state table, then you can, given a particular input sequence, you can then see what the system does. So one could certainly do that. The problem with that is that you're kind of getting swamped with all these zeros and ones and way too many states and all, and kind of the big picture kind of doesn't pop out. So what people found very useful was to kind of capture this, that how the system is moving from one state to another in visual terms. It's just friendlier for us as humans. So what happens now is that there is another formalism which gets used, which is called state diagrams, or you would often, they're also called finite state machine or finite state diagrams. A whole bunch of terms describe this, but common to all of them is this notion that I have a graph in which each node represents the state of the system. So since we have two state, in our example, I have 2 bits of state, I have 4 possible states, so they are listed out here, 0, 0, 0, 1, 1, 1, and 1, 0. And then the edges indicate how we can move from one state to another. Now, in the worst case, if you're in a given state, under different conditions, it may be possible for you to move to any of the remaining states. So you can have a fully connected kind of graph, but rarely is that the case. Like, for example, in a counter, we were always going from state 0, 0 to 0, 1 to 1, 0 to 1, 1 back to 0, 0. So a very limited set of transitions were possible. So in each edge, there are 2 things that we capture. Number 1, which state we are moving to. So like, for example, this particular edge that we see out here, I'm referring to this particular edge, is telling us a couple of different things. So first thing it's telling us is that this edge goes from state 0, 0 to 0, 1. Second thing it's telling us is that under what conditions are we going to take this transition. The condition here means what should the value of the input be. So it's basically telling us that I'm going to take this transition if the value of input is 1. So this represents input. And we can see that state 0, 0, input 1, I want to go to 0, 1, right? This particular row corresponds to this particular edge. So that's one thing. The second thing we see is after the slash sign, it is telling us, and while doing so, what should the output be? So in this particular case, our state table tells us that the output should have been 0, and therefore you see a slash 0 after that. So input condition slash output value. That is what you see on each edge. So now, how many different edges can I have out of a node in something like this? So as many different cases of inputs that may occur. So in this particular case, I have a 1 bit of input. So I really have 2 possibilities, input equal to 0 or input equal to 1. So I can have at most 2 edges going out of a state. I may have only 1 edge also, because I may not care about the input. I may say, whether input is 0 or 1, just move to a different state. Okay, in which case there will be a single edge going out. But at most I can have 2 edges. If I had a k-bit input, then I can have at most 2 to the power k edges going out of a state. But again, in general, in any realistic system, you would have a lot fewer. So you would see in this particular case, what's happening is that if the input is 1, I'm moving to a state with a numeric value which is 1 higher. If on the other hand, if I'm in state 0, 0 and input is 0, I kind of stay put out here. If on the other hand, I'm in one of these states, 0, 0, 1, 1 or 1, 0, then if the input is 0, I reduce, my next state has a numeric value which is less by 1. So this is kind of, if you stare at it, it's sort of acting like a counter which can go up or down also, right? So what's happening is, if the counter, if the state is already 0, and if my input is 0, I stay put there. If input is 1, I increment the state by 1. If input is 0 and I'm in any other state other than 0, 0, then I reduce the state count by 1. Okay, so it's kind of a up counter, down counter, and stay put at 0 kind of thing that is happening. Now, the main thing that I wanted to get out was that I'm showing you that looking at this kind of a diagram gives us a lot more intuitive sense of what the system is doing than if you were to look at that state table, that pattern that the states were moving, incrementing or decrementing. That was not obvious looking at the state diagram. It was not obvious by just doing a simulation. Whereas looking at this kind of graphical stuff makes it a lot easier to visualize. So what happens is that when it comes to designing state machines, a very common way is to just draw the state diagram of finite state machine. There are specialized tools which let you do it. So what you can do is you can literally kind of draw a graph like this with edges and all, and then it spits out an implementation. It basically outputs description in terms of a state diagram like this, or perhaps a description in one of the hardware design languages, or even an implementation in C or Java or one of these things. So it's a very common kind of mechanism which is used. Of course, the tools have a lot more extra features and all, and in fact, it's used in software world a lot. A lot of software systems are also nothing but finite state machines. They're implementing, they get signals from outside, they operate on it, they create output. So there are a lot of these kind of tools available which let you write a state machine in a graphical fashion and then spit out C code, Java code, hardware, gate description to unfortunately for us, none of the good tools are freely available or easily available, so we don't get to use one in this class. But If you were to take one of the graduate classes, or in EE, there's going to be a digital design sequence, a capstone course. There you get to use some of the more professional category kind of tools, more complicated, so we don't introduce them at this stage. So that's one way to design these things. Of course, you can also design them by doing this state diagram, but it's kind of rather painful, particularly for big systems. Imagine now, even with the imagine now, let's say you are writing the state machine of a 16-bit counter. How many states will it have? 2 to the power 16. That's how many nodes in my graph? 65,536 or something like that. So clearly, visual stuff is okay for simple things, but if you have lots of states, even this visual stuff doesn't quite work out. And that's when you move to the next level of designing these state machines, which is essentially you write a piece of software. Okay, you start putting variables, much like we do in the program. So there are some tools. So kind of really complex state machines, you either write them as a program, and then the tool kind of gives you the hardware from it, or you do it visually, but then you also introduce some program variables. So you'll find these kind of tools if you happen to go to this industry where kind of more complicated state machines could be done. There is no way you're going to write down all those states as bubbles. It just doesn't work that way. Okay, so that's a very high-level thing about state machines or state diagrams. So each bubble, each node represents a state, and each edge represents a state transition, and each state transition is described as input condition / output value. So in our particular case, the input condition was just a value, so it's basically saying input equals to that. But sometimes it could be a Boolean expression, for example, across the input variable. So this first thing could be a Boolean expression over the inputs. So it basically says under what condition am I taking this particular edge. And the second one is basically telling me what the output should be. Or if I have more than one output, it would have more than one bits in there. So let's see how it kind of plays out in designing something more complicated. So now we are going to look at a synthesis problem. So we are given a problem description, some specification from, and you have to design a system. And there's a complex system. It has history, so you need state. And now the thing is, you have to again kind of analyze it, and sort of, as I've often said in the past, instead of diving into gates and flip-flops now, first think about the algorithm. Now the counterpart of algorithm when it comes to sequential systems is to first think about what my state diagram will look like. Okay, you have to first think of what are the states and how am I going to move between these states. Once you have done that, then getting an implementation out of it is basically straightforward. You just kind of follow some mechanical steps. So the hardest part where kind of your intuition and sort of thinking is needed is to come up with that initial state diagram. So the problem in this case is that you have to design a really simple, naive traffic light controller. We encounter them all the time, and we never think about it, but I mean, the simple traffic light controllers that you encounter somewhere on either underground or right on the there's a little microcontroller which is controlling those traffic lights. Sometimes you also have sensors on the ground. I'm sure you've encountered them, those magnetic loops. When your car goes over it, then it gives it priority. Other fancier stuff nowadays, emergency vehicles have a wireless transmitter, and when they're approaching, the traffic light turns green for them so that they can race through. In city of LA, all traffic lights are now connected to a network, and somewhere in the city, there's a central place where all those traffic lights are monitored, and based upon traffic conditions and all, they kind of adjust their timing parameters so that the traffic keeps flowing. So traffic light it's a traffic engineering is a complicated thing, you know. This is the simplest of the traffic controller you can imagine. So what we have is a crossing with sort of 4 roads meeting at a junction. And what we want to do is to design a strategy for controlling these things. What we are given is, so we have an east-west route and we have a north-south route. And what we have on the east-west part are a couple of sensors, car detectors, which are shown by this sensor and this sensor. These car detectors feed into an OR gate that's given to you, and then I get a signal called car east-west. So I have a signal. You can think of like the two sensors are coming together, and they are giving me this signal, which is saying that there is a car on the east-west route. Okay, there is no such sensor on the north-south one. And then I have a clock signal. The whole system is clock synchronous. There is a reset signal, and then I have to control the lights, and I have 6 lights, 3 for east-west direction and 3 for north-south direction. So 6 signals controlling the 2 reds, the 2 greens, and the 2 yellows. So a total of 6 signals. Now, what we have to do is to, we are given some specifications, some properties that we want the system to have. So what we want is the following, that if there is nothing happening, we would like north-south direction to have priority. So if there is no car on the east-west route, whatever, then basically the traffic flows through north-south. So north-south is some sort of a main street. So by default, that's traffic flow. Second condition, if light is green or yellow in one direction, it must be red in the other direction. This is kind of just a basic sanity check. You don't want cars to collide. Okay, so if I have given green to the north-south flow, then east-west must be red, or if I have yellow on north-south, east-west must be red. So it's okay to have both sides be red, but it's never okay to have both sides be yellow and green. Okay, so if one side is yellow-green, the other side must be red. Light must be yellow between changing from green to red. This is how we normally expect. So green, you go to yellow, then you go to red, then from red you can go back to green. So that's another constraint we have. And finally, if there is a car waiting on east-west, so if our sensors indicate that a car has arrived on the east-west route and is waiting, then east-west should become green before then we go back to green north-south. So the idea being that if there's a car comes on the east-west, then we are going to turn the north-south to be red while obeying the conditions out here, the preceding conditions, and then turn east-west green, let the car go through, and then flip back to north-south green. So that's the behavior we want. And what we have to do is to design that state machine. So state machine, any state machine would have inputs, outputs, and states. So in this particular case, we have to think about what can be our states. What are the possible configurations of the system? So so the current state of the system, since there are 3 lights in each direction, so you could say I would have 9 possible current states of the system, right? I mean, east-west could be one of 3, and north-south could be one of 3. So 3 times 3, there are 9 possible combinations. But not all combinations make sense in our particular case. For example, we already know that the system should never be green-green. It should never be green-yellow. It should never be yellow-green. It should never be yellow-yellow, right? So 4 states are immediately ruled out of 9, right? So we are left with 5. Okay. Then comes this notion that would we ever have red-red? That doesn't kind of make sense because as I'm transitioning one from 1 to red, I can bring the other one out of red. So red-red will never occur either. So that means I am now left with 4 states. and these are the four states. I am green north-south, and therefore implicitly red on east-west. I am yellow on north-south, implicitly red on east-west. I'm green on east-west, implicitly red on north-south, and I'm yellow on east-west, implicitly red on north-south. So there are only four possible states that a correctly functioning version of this system could be in. So we started out with, there are in principle 9 possibilities because I have 3 colors in each direction, 3 times 3, 9. We ruled out all the dangerous possibilities, so couldn't be red, green, 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 yellow, yellow, green, yellow, yellow. So 9 minus 4, 5. And then we ruled out red, red because that seems superfluous. That would result in an inefficient system. So then we are left with 4 possibilities that the system can be in. So this kind of mental kind of analysis is one of the very first things you would have to do. Faced with a problem, what's really the state? Okay, as what state the system could be in. So in this case, we kind of reached the conclusion that these are the 4 possible states. We have 2 inputs. We have the input car east-west, which basically says is a car waiting on the east-west route, and then there is a reset, which basically says return to initial state without going to yellow. So reset basically immediately takes our system so that east-west is red, north-south is green. Output, I have 2 3-bit traffic light signals. So for example, 100001, if my output is this, it's basically indicating that north-south is green and east-west is red. So let's see. Let me just make sure. Yeah. So the second one is east-west. The first one is north-south, and then it's green, yellow, red. So that's our. Sorry. Okay, so first cluster of 3 bits is going to the north-south lights, controlling green, yellow, red. The next 3 bits are going to east-west, again controlling green, yellow, red. This coding, if you recall, is one hot coding, right? I mean, if you think about it, again, in any given cluster, green, yellow, red, only one of them could be on. So I have a total of how many I have a lot fewer possibilities of, right, but I'm basically dedicating 1 pin for each one of the light colors. Okay, so I could have encoded it more compactly instead of using 6 bits, but then I would need a decoder on the light side. If you think about like how these lights would be designed, right? I mean, they'll typically be a light bulb, and you'll have a switch that you can control, a relay, for example. So it kind of makes sense to just have 1 wire for each light bulb. So I have 6 wires going 1 to each of the light bulbs. So in this case, 100001 is saying north-south is green, east-west is red. Likewise, if I have 001, 010, it's saying north-south is red and east-west is yellow, and so on and so forth. And again, not all combinations will occur because we know that there are constraints that this system has to meet. So faced with a problem description, the very first thing you have to do is kind of do all this housekeeping. What my inputs are, what my outputs are, what are the states, and for that you have to think about what states make sense to have in the system that will capture everything. Then the next step becomes drawing the state diagram. So let's see how we end up doing that. So once we have figured out our state, I have 4 possible questions.
Why do we have to go back to reset the initial state?
Oh, it's the problem has given that to us. Typically, it might be that after a power outage, I'm kind of just bringing my way out here. But let's imagine after a power outage, I just want to make sure the system goes to normal place.
But even if you don't reset to a certain initial state, it can always operate normally after a few cycles. Will it start the unwanted?
No. So imagine my system comes up after a fresh power up. It could be any of it could be in any state. In fact, it could even be in a dangerous state conceivably. So by reset, I just make sure that it comes to a state. So I have four valid states in the system. We label them as green north-south, yellow north-south, green east-west, yellow east-west. So these are just mnemonic names we give to the states. And then one thing you can see is that when I'm in green north-south, my light value should be 100001, right? Green should be north-south should be green, east-west should be red, and likewise in each one of these states. So here you see that instead of putting the output values on the edges, I'm putting the output values in the nodes, in the state nodes. What kind of state machines does this do? If I'm putting them on the edges versus if I'm putting the output value on the node of the graph, what does it indicate? More annealing. So what is this one? More, right? Because the output depends only on the state. So a more machine is usually drawn this particular way. That is, we put the output in the state thing. So this indicates output depends only on state. So this is more. Now you could have drawn it the previous way also by putting the output on the edges. All that would mean is every outgoing edge will have the same output, right? Because that means it's independent of the edge. So it's much better, instead of cluttering the edges, it's much better to kind of put the output values inside the bubble for the state. Okay, so I have those four states. I have the outputs taken care of. The only other part we need to take care of now is what happens.
Yeah, so the reset is also an input.
Reset is also an input.
That will immediately affect the output, right?
That reset will not immediately affect the output. It will affect the output at the next clock rate. Okay, and which is fine because I mean, if you think of it, your clock take in these systems is going to be few megahertz, right? I mean, so that tiny little one clock cycle delay of a few microseconds at best, perhaps not even that, is minuscule relative to the system you are designing. Okay, so yes, because we are making a mode machine, therefore the output will only be affected after a clock cycle delay, but our clock cycle is so much faster than the speed at which cars are moving and all this inconsequential. Okay, in some other systems that may be an issue, not. Okay, so going back out here, so the only remaining thing at this stage is to figure out how do I move from one state to another, and we were given several things. The first thing to take care of is reset, right? So reset was saying, independent of whatever state I may be in, I want to move back to the default state, which is green north-south. So you see out here that from the other three states, yellow east-west, green east-west, yellow north-south, if the reset signal is high, so you see reset here, you see reset here, we move back to green north-south. On yellow east-west, we don't put reset because after yellow east-west, we know always it has to be green north-south. So there is a single edge coming out of yellow east-west, which is basically taking us back to green north-south. Now let's look at green north-south. So if I'm in green north-south, and if there is no car on the east-west segment, I stay put, right? I have to stay in the same state. So that's what you see out here. It's basically saying if there is nothing on the east-west or reset is high, then I stay put in the green north-south. There is a self edge out here. If there is a car on the east-west, that means car east-west is high and reset is low, so I'm not resetting. In that case, now I have a car on the east-west segment, so I'm going to move to yellow north-south. So I'm going to take the green, I'm going to turn the green to yellow on the north-south direction. So I move from this edge out. So this is the path I'm going to take, right? This is basically saying if car on east-west and no reset, right? That's what this condition is saying. And here we do not have slash output because this is a more machine, so I have put the output inside the edge already, inside the node. Another notation that you go ahead.
Actually, the clock is not fast.
Huh?
Actually, the clock is not fast because the clock is the duration of switching.
Yeah, you're right. So what he's pointing out is that the clock here has to be slow because I'm keeping the lights on only for one clock cycle. So if they're truly microseconds, okay, granted. So these are liberties of a simpler example. But you're right. Okay. So we move from green north-south to yellow north-south if the reset signal is not present and there is a car on the east-west segment. So we do that, and otherwise we stay put. Sometimes, just by way of notation, you would see that this self edge is not written. And if the self edge is not present, then basically the implication is that if none of the conditions which leave the state are met, stay put there. Okay, so what I mean by that is, from this state, there is only one outgoing edge, which is this one, which says car east-west and no reset. So in many cases, you would see that they don't bother drawing the self edge because it's implied. It's basically saying if none of the outgoing edges are taken, then you stay put wherever you are. And the reason they often do it is, people often do it is because it reduces the clutter. There's an implied self edge, which basically says if there is nothing happening which takes you to a different state, then you just stay put.
Does that mean you could just take out that self edge then?
You can take out that self edge, but now for purposes of this course, if you decide to do it, then I would like you to put a notation that you are doing that. Okay? Because so that you're conscious about it, because otherwise it's also a source of mistake. Okay. So, but generally speaking, again, for purposes of this course, I would like to draw all the edges, including the self edge, even though it results in a more cluttered state machine. That's normally the case with most tools also, but some tools do provide this capability that you can skip the self edge. Okay, going back out here. So once we reached yellow north-south, if there is a reset, I go back. If there is no reset, then after one clock cycle, I move to green east-west. And this is a point that he was making that, hey, I'm staying only for one clock tick in this edge, so my clock has to be slow. So if not reset, I go to green east-west. Again, if the reset comes, I go back immediately. Otherwise, if no reset, I move to yellow east-west. And then finally, I go back to green north-south. So that's kind of my very contrived, like.
What is that?
Which one?
The one from yellow east-west to green north-south.
Oh, this one? This basically says you spend a clock cycle out here and then unconditionally move. Yeah. So star basically is a way of saying that under any condition. Okay, so yeah, go ahead.
Is it better if we put the edge from YNS to YEW?
Edge from YNS to YEW without going through green?
Because the east-west direction, we should also get yellow line.
Okay, so in this case, what's happening is that we are putting so from YNS after YNS north-south will turn red, and we are giving green immediately to the other one, right? So when you are turning green, then you don't go through yellow in that direction. So it's like red, green, and from green to yellow, back to red. So any given direction, what you will see is red, go to green, go to yellow, go to red.
So I'm asking, should it be better to go from red to yellow and then to green?
No. Firstly, that's not how it happens, right? I mean, if you look at normal traffic lights, from red they go straight to green, right?
Why do we need reset from the YNS to GNS or from GW to green?
Because the spec said that whatever whatever state you be in, if the reset comes, you have to immediately, as in the next clock
But
tick.
normally it won't happen, but like in real life, it's not gonna happen, right? Or something.
No, so so the purpose of these reset signals typically is that after the initial power up and all, you want to make sure that the system goes to a proper state, a known state. So that's really the only thing. That's the only time after that initial use of reset, you'll probably never use the system use that input. Okay. Any other questions? So again, as you saw, the process of designing that's the part which I want to focus most on, which is given this kind of messy problem description, probably will be given to you by like in a real environment, some other group, a customer, a client, whatever. They'll give you these fuzzy set of descriptions. Some of them are constrained on your system, some of them what your system should do, and then what you have to do is kind of distill it down into what my inputs are, what my outputs are, what states do I have, how do I move between the states. Okay, that's really kind of what you are seeking, and that's really kind of the equivalent of the algorithm for a sequential system. Once you have this, then actually so coming to this state is where your design skill comes in. Once you have this, taking it to an implementation, there are tools that can do it for you, although you have to do it manually in this course. But again, these things can get very complicated. There are protocols and all where there may be hundreds of states. So manually designing them could be very error prone. There are all sorts of sophisticated tools which help in this process. And like I said, they can spit out correct by construction, hardware implementation, software implementation, all sorts of things. Even, I don't know, some of you may have used like MATLAB and these kind of tools, perhaps in some courses. They have these kind of packages built in. You essentially draw the state diagram and it can generate stuff for you. There are lots of commercial tools. In the book, you have probably noticed the Verilog examples that they have. You can write a state machine in programming language like Verilog, so that's also possible. So there are all sort of ways of doing it. But really, kind of from that some plain English description of your system, coming to this stage is what really you need to know how to do well. The remaining part, again, in your professional life, tools will take care of it for you. Okay, so now let's see how we would now nevertheless do that manual part subsequently. So now to keep life simple a little bit, we are ignoring the reset signal. Most of you were unhappy about it anyway, so that's great. So we have now the state machine without the reset signal. So what we are left with is this. If the sensor says there is a car on the east-west, we basically cycle through. So we turn the light yellow north-south, then we turn the light green on east-west, then we turn the light yellow on east-west, then we come back, and then we stay put there until the next car comes. By the way, do you see a problem with the state machine in terms of real life?
What happens if the east-west is just making like a right turn, and then they're gone immediately, right? They'll make a right turn, and then
No, they are not allowed to. So this is in a state where no turn on the
This is getting a huge priority on the east-west. So
Exactly.
if there's a car,
So if there's a lot of traffic on east-west, the north-south will get stuck. Okay, so that's going to be a real-life problem on this one. And we started out with this notion that north-south is the main street, but so in real life, you'll probably also say that I have to stay in the very first state for some time duration, so that those cars get a chance because there's no sensor there. But anyway, that's an aside. Okay, so this is our simplified no reset version of the system.
that way to trigger a particular state with two clocks,
With two clocks.
two different clocks.
Expand on it. So what do you mean by that?
Because I want the reset to be fast and the transition to be slow.
No. So firstly, you design these systems with a single clock. Okay.
But I can divide it.
You could divide it. and then you could feed it, it will lead to a very hairy design. So what you would normally do is if you want to stay put in a state for a longer time, so you use your fast clock, and then you use some sort of a timer. So you'll say, count 5 seconds for me, and then send me an input.
Yeah, but for the state, I want the reset to be faster than the transition.
Right. So what you would do is you will have a very fast clock corresponding to reset, and then for the other things you are going to count out time. You make sure that you spend some time in the
But we are driving the same state. I'm asking, can I use the two different clocks?
you will not use 2 clocks. I mean, I guess you can come up with a scheme to do it, but it soon becomes very hairy and it's not kind of an advisable thing to do. So, one thing I cannot emphasize enough is the following, that engineering these systems, they are very complicated. I mean, not these toy examples I'm giving you, but systems with hundreds and thousands of states and all. So it's usually frowned upon to adopt tricky low-level solutions, because if it's kind of the equivalent of you're writing some code and you come up with some cute little trick at the code level which can do some funky stuff, but it would be impossible for the next developer to understand. It will break down. So generally speaking, particularly in industry practice, and also actually in research and all, put your creativity at this level, like where you are thinking about the algorithm and all, and keep your low-level implementation simple and robust. Because while you may save some transistors here and there, but generally speaking, they make your design hard to maintain, hard to understand, this overall tricky. So your creativity is better focused on the algorithm and the architecture. You can do a lot more optimization there. So this is kind of a general statement, nothing to do with this course specifically. In general, if you're writing the software and all, optimizing some individual expression is probably not going to have a whole bunch of impact as your high-level algorithm. Okay, so moving on. So we have the state machine, this diagram. So then I have to now find the gate level implementation of it. So what we'll now do is we'll basically create this state table, except that right now we only have names for these states. I have not given any, I have not said that how do I represent those states. So I'm going to keep a state table, but in terms of names. So I would say current state is GNS, YNS, GEW, YEW. There are 4 possible states. Next state, depending upon whether the sensor says 1 or not, so case when sensor is 0, case when sensor is high, I basically have the next state. And then output is only a function of the current state because it's a mode machine, so I have the output listed out here, which again in terms of symbolic names looks like this. So at this stage, I have not made a commitment as to what bit pattern would be used to represent these states. All I know is there are 4 states, and I have given them names of GNS, YNS, GEW, YEW. Since I have 4 states, I could use 2 bits for them. I could, let's say, call them 0001, 1011, or any other, or maybe I can call state GEW to be 00. I could choose a redundant representation. I could use a one-hot coding. There are all sorts of ways I can code 4 elements. We saw that very early in the course also. So there is nothing, at this stage, there is nothing which says that any particular state should be represented by any particular bit pattern. So what I have, therefore, is this table where state names appear as just symbolic names. Okay. So then the very first problem you face is, how do I represent the states? I have to map these states to bits. So this should remind you of module number 2, where we had looked into representing information. I have a set of values, and I have to find a representation for them. And there were compact representations. There were more redundant information, things. So we have to assign values to each symbolic state. So I have 4 states, and I have to encode them. I have 2 signals in my system, current state and next state, which uses those. So with the usual caveats that we have seen, there are many possible ways of encoding them. For example, this is one arbitrarily chosen coding. I can represent them as GNS as 100, YNS as 0100, GEW as 0010, YEW as 0001. This is our good old one-hot coding. I could again kind of represent something else, but perhaps the two most common forms of encoding states is either doing one-hot coding or doing the fully encoded, so minimum number of bits that you need, in this case 2 bits, encoding using them. Depending upon what kind of coding you pick, your combinational logic may be hard or easy. So it's a little bit of a tricky game. How you choose, what representation you choose for your states affects how the complexity or the cost of your combinational logic. And there is no kind of direct answer to it. When you are doing things manually, oftentimes one-hot coding is very easy. If a tool is synthesizing stuff for you, they can actually hunt for the best representation. So some of these tools are smart enough, they can go around and figure out how best to represent each state, how many bits to use, so that overall implementation cost is minimized. But in this case, let's say we pick this one-hot coding. So I have 4 states, one-hot coding, so I need 4 bits, and that's the representation I have. Then so I have one-hot coding, and now I can. So a nice thing about one-hot coding of states is that we can actually come up with a state, come up with an implementation almost kind of directly without kind of going through a whole lot of labor. So for manual design, it works out great. So the way it works is the following. So I have one-hot coding. I need 4 bits, right? 4 states, 4 bits. As many bits, as many states. So what you do is you start by, for each state, you put a flip-flop. And since it's one-hot coding, so we'll make, what it means is that one and only one flip-flop would be high at any given time, right? That's the definition of one-hot coding. I have 4 states, 4 flip-flops. Exactly one of them would have 1, the remaining 3 would have 0. So I put a flip-flop for each state. For GNS, I have this flip-flop. For YNS, I have this flip-flop. For GEW, I have this one. For YEW, I have this one. If the system is in the state GNS, then the first flip-flop will have a high value. If the system is in YNS, then the second flip-flop will have a high value, and so on and so forth. And then the trick is you have to kind of decide what should the next value of each flip-flop is going to be. So looking at the state machine, we can say that, look, if I am currently in the GNS state, then if the sensor says 0, then I have to stay out here. If I am in the YNS state, I will unconditionally move to the next state. So if I have a 1 in the second flip-flop, in the next clock tick, that 1 should move out here. And so forth. So let's see how to make it work. So this is what this is what the state transition circuit looks like. So let me kind of walk through this thing. So let's look at firstly this edge, so let's look at this edge. So it's basically saying that if I am in YNS, which means that I had a 1 out here, then in the next clock tick, so I start out with this. I have 0 here, 1 here, 0 here, 0 here. I'm in the YNS state. Next clock tick, I want that 1 to move to the next flip-flop, and I want all the other flip-flops to become 0, right? After I need to move to the state GEW, which is 0, 0, 1, 0. So what that means is that this one, by the way, again, those of you who are missing it, these are all flip-flops. There's a clock here, there's a clock here, there's a clock here, and likewise there's a clock here. Okay, so all of those boxes are flip-flops. So when the next clock tick comes, what will happen is that since I have this flip-flop was 1, and therefore there's a 1 on this wire. So next clock tick, this 1 will move to this flip-flop. This flip-flop will read a 1. So next clock tick, this guy will go to 1. Meanwhile, I had a 0 out here in this wire. So this guy will stay. This guy was 0. It will move to 0. It will move to 0. So its next value will remain 0. This wire was 0. So I had a 0 out here. And this guy was 0. So through this AND gate, I get a 0 here. And I have 0 or 0. So again, I get a 0. So I stay at 0. So this guy stays at 0. And then finally, I have a 0. I had a 0 here. So this AND gate would produce a 0. So this guy will become 0. So for 1 to move from flip-flop number 2 to flip-flop number 3, I just need a wire. Same thing for flip-flop number 3 to 4. I just need a wire. There is nothing affecting it. There's a star out here. This final flip-flop, this very first flip-flop is a tricky one because now I have to take into account the sensor. So if the sensor is high, then I need to move to the next state. So if you so if the sensor was high, so if this guy was 1, then you would see what will happen is, so let's say I start out with, so I'm going to, okay, so let's say I start out with this. I'm in 1, 0, I'm in this state. So I'm in the state GNS, so flip-flop number 1 is high. Now let's say car east-west is 1. So what would be the input of the second flip-flop? Anyone? So input of the second flip-flop would be 1 and 1, which is 1. And therefore, at the next clock tick, this 0 will become 1. This 0, because it picks up the 0 out here, go to 0. This 0 becomes 0. And finally out here, I have a 0 out here. Car east-west is high, so input of this AND gate is 1 and 0, so it's 0. So I get a 0 out here. And this 1 therefore will move to 0. So when car east-west is high, I move from 1 0 0 0 to 0 1 0 0. That's what we want. And again, going back, let's try when car east-west is 0. If car east-west is 0, then we want to stay put in GNS. So that logic will follow also, because what is happening now is this AND gate is seeing a 0 at the input. So it will have a 0 out here. So this 0 will remain 0. This 0 remains 0. This 0 remains 0. And then finally this guy. So I have a 0 out here. There's a 1 out here. So this AND gate will output a 1. And therefore the OR gate will output a 1. And therefore this 1 will remain 1. So what you really are kind of doing out here is that for each one of these flip-flops, you are basically looking at the incoming edges and then saying, okay, if the under what condition do I kind of stay, what happens out here? So if I look at the second flip-flop, I come to this second state if I was in GNS and car east-west was high. So therefore, I have this AND gate, which is saying if the GNS flip-flop is high and car east-west is high, then I should get a 1 out here. This guy, flip-flop number 3, says I should get a 1 here if the previous state was YNS. So I just have a wire coming in out here. Likewise, fourth flip-flop says I will come to YEW if previous state was GEW. So I have GEW coming out here. And finally, let's look at this logic, GNS. GNS basically says I come to GNS under two conditions. If previous state was YEW, okay, so therefore I have an OR gate because I have two possibilities, OR gate, so I have a wire coming from the flip-flop of the previous state, or I am in GNS and car east-west is low. So therefore, I have an and, I am in GNS, which means I have this feedback loop, and car east-west is low, which means I have a car east-west with a complement. So literally by looking at your state diagram, you can kind of draw out this logic without doing any Karnaugh map synthesis or anything like that. Of course, all of it has a cost. I am using one flip-flop per state because of this one hot coding, but you can just visually kind of write down kind of the state, next state logic basically without having to do any optimization. So again, what you are looking at is under what conditions for the next clock cycle I'm going to be in this state. And for these three states, for YNS, the answer was I'm going to be in YNS in the next clock tick if in the current clock tick I am in GNS and car east-west is high, which is why I get this AND gate out here. For GEW, I say I will be in GEW if currently I am in YNS and therefore all I have is a wire. For YEW, again, I will go to YEW if currently I am in GEW. That's the only condition, so that's why there's a single wire out here. Finally, for GNS, we say I will next clock cycle I will be in GNS under two conditions. So therefore, I have an OR gate with two input. One condition is that previously I was in YEW, and therefore one input of OR gate comes from the YEW flip-flop. And the other condition is I am in GNS and car east-west is low, and therefore I have this AND gate. So with one hot coding, we should be able to manually work things out. When it comes to exams and all, if you cannot create a more optimal state machine, this should be your backstop. You should always be able to create a one hot coded state machine, just literally kind of essentially rejoin your state diagram directly for the key. Now, what we have not done thus far is given you the output logic, right? Our two sets of red, yellow, green lights. We haven't done anything about them, so I also need to put some additional logic for doing it. But in our case, it's very simple. Looking at this, you can say you can see the easy direct mapping. So the next slide kind of does that. To control the north-south light, so the north-south light, is green whenever I am in state GNS, right? That's the only one where this is high. So you see the green light is directly controlled by this wire, right? So it's green whenever I'm in GNS. It is yellow whenever I'm in YNS. So you see this controlling the yellow. And finally, it is red under two conditions. I am in GEW or I am in YEW. So what you see out here is the red is controlled by red is controlled by this structure. So it's basically saying red is high whenever. Pardon me? Yeah, when green and yellow is off. So we are kind of relying on that property. Okay. So those guys. What about this guy? So east-west is green in this particular state. So GEW. Let's move on to the next one. So east-west is green when this flip-flop is high. So this is getting us the green part. Then yellow comes from this guy, yellow east-west. So we just pick that one up. And by the same logic, red is whenever it's neither green nor red. Neither green nor yellow. So again, manually kind of relatively simple to kind of pull this thing for, make this thing happen. So one hot coding, literally, you drop once you have your state diagram. Going from that to an implementation tends to be pretty straightforward. Of course, if the number of states is large, it can still be messy, but you don't have to go through much of like synthesis or anything. That is a one-to-one mapping that is happening. Okay, and of course I have the clock, which I was not drawing thus far. Okay, so that's one possibility. But we are now using 4 flip-flops, and flip-flops can be pretty costly. So then the question becomes, and if n is large, the saving could be huge. Let's say I have 100 states, then if I do one hot coding, I need 100 flip-flops. If I do fully encoded coding, how many flip-flops do I need? Anyone? Come on. 7, right? So there's a huge difference between 7 and 100, right? So larger number of states, you might want to not do one hot coding because it could be extremely inefficient doing it. So in a small example like this, the difference is probably not going to show up much. So let's say we decide to do the fully encoded type states. So the 4 states, I can represent them in 2 bits. So 0, 0, 0, 1, 1, 1, 1, 0. And then, of course, the question becomes which state should be assigned to what. I mean, I have a whole bunch of possibilities. So we pick one. So we say GNS is 0, 0, YNS is 0, 1, GEW is 1, 1, and YEW is 1, 0. And now I have to design this combinational logic which would implement the logic when the state and the next state are represented with these particular bit patterns. So I have now a combination logic which has one input, the car east-west, then it has 2 bits of state, so total of 3 inputs, and then it's outputting 2 bits of next state, and it is also outputting 6 other signals, one for each one of the light. So it's outputting 6 plus 2, 8 output signals, and it has 2 plus 1, 3 input signals. So that's the combinational logic I have to design. And you could do it using your Carnot maps and stuff like that. So this is our new state diagram, except now instead of using symbolic names for the states, we have put the actual bit patterns for the state. So the 4 states 0, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. Under the, depending upon what the sensor said, we have 2 possibilities, and then finally the output is represented this particular way. So now this problem is one of, it's kind of very similar to what we did in Logisim homework, for example, where I have a function where I am controlling, I have a bunch of outputs and I have several input pins. I have in this case specifically 3 input pins, 3 input signals, and I have a total of 2 plus 6, 8 output signals. And you can design them using K-map, you can design them by Boolean algebra operations, or if it's a Logisim assignment, you can just use Logisim's thing, or other ways that I can understand. Yeah. I have one external input, which is car east-west, and I have 2 bits of current state. So the combinational logic I'm designing has 3 inputs too, right?
So is it true that generally one hot coding is more easily to design?
For humans. For humans, if you're manually designing it. See, for a software program, all these things are.
For one hot, we can just by looking at the state diagrams.
You can just draw it out. Yeah. So that's what I meant, like in exam settings and all. If the number of bits is large, it might be tricky to kind of do an optimized implementation. So at least get if you're struggling with kind of an optimum implementation, at least do a one hot coded implementation. You get frustrated. A lot of the credit depending upon it. Okay, but again, sort of the distinction between one hot coding and versus others really matters when you're designing manually. When you are designing using software tools, they can optimize for you. Okay, question.
Why is car east-west 2 bits again?
Car east-west is 1 bit.
Okay.
Car east-west is 1 bit. These 2 columns correspond to what the next state is, right? So if car east-west is low, then the next state is this way, and otherwise this way. Okay, so to implement these, I need a whole bunch of Carnot maps. Particularly, I will need 8 Carnot maps for 3 inputs each, right? Because I have 8 outputs that I have to generate. the 2 bits of next state, and the 6 bits of output. So here we are kind of showing it only for the next state functions. So the Karnaugh maps for the 2 bits of next state look like this. You can kind of do the usual clustering. It looks like this. Let's see. So eventually, if you kind of work things out, you would see that the logic equations end up looking like this. So next state 1 is S0. Next state 0 is S0. S0 is the 0th bit of the current state. S0 or car east west and not S1. So I will not sort of walk through it. This is stuff that you should be able to do it based upon what we have learned thus far. But basically, we have 2 Karnaugh maps that I have shown. One for upper bit of next state, one for lower bit. I have not shown the Karnaugh maps for the 6 output bits. So that you can draw in a similar fashion, and eventually you will end up with those equations. And again, I would emphasize that you need to know how to do this thing. Okay. Again, in this course, the idea is you have to get comfortable with the fundamentals behind how these things work. Even though in your professional life, designs are way too complicated to do manually. But under the hood, the tools do this kind of analysis. So when you put everything together, we end up with a system like this. So now I have 2 flip-flops corresponding to the 2 states, state bit number 1, state bit number 0. I have those states are controlling the lights, and those states are also feeding back and giving me the next state. So this is next state 1, and this is next state 0. And so every clock tick, new next state kind of the next state gets loaded into the flip-flops, and so looking at this, it's unclear whether this is necessarily better than our one-hot coded design. So if we go back to our one-hot coded design, this was our one-hot coded design, which had 4 flip-flops, 5 gates, 5 2-input gates, versus this design where I have 1, 2, 3, 4, 5, 6, 7, 7 2-input gates and inverter. So I'm paying the cost of an inverter plus 2 additional gates, and I'm selling 2 flip-flops. So you're ahead on this one. A flip-flop is worth a few gates. So at the cost of basically 2 gates and 1 inverter, I'm selling 2 flip-flops. So this seems to be kind of a better overall from a cost perspective. So even in this small design, except that we had to put in a lot more effort, as you can see, right? All those K-maps and all. Whereas, so if you're under time crunch, you're designing something, the one-hot approach is a lot quicker to do. So let's look at, yeah. Huh? I just counted the gates, okay? So again, here, so I have 2 flip-flops plus 1, 2, 3, 4, 5, 6 2-input gates plus 1 inverter, okay? My previous one-hot coded design has 4 flip-flops plus 1, 2, 3, 4, 5 2-input gates. Right? 1 here, 2, 3, 4, 5. Yeah. So 4 flip-flop plus 5 2-input gates versus 6 flip-flops. Sorry, 2 flip-flops, 6 gate plus 1 inverter. So I guess one gate plus 1 inverter is saving us 2 flip-flops. So this would be a better. Yeah.
How come the inverters on the gates don't count towards the counter inverters?
How?
The bubbles, those don't count as...
You are right. The thing has to do with Okay, so let's do a more accurate code. Okay, so let's try it. Okay, so okay, so firstly, this is just a 2-input gate. This is just a NOR gate, so I'm still going to count as 1. I need an inverter here. I need an inverter here, and this inverter actually is the same as this inverter, so I actually don't count for it. Okay, so I'm left with this inverter. Yeah, so I need 2 inverters here, and I need an inverter here, so it will be 3 inverters. And we go back out here. I don't need to count these 2 inverters because this is just NOR gate. Ditto out here. I need 1 more inverter, so it would be plus 1 inverter. So I am saving at the cost of 1 gate plus 2 inverters. I'm saving 2 flip-flops. You are still going to be well ahead. One thing I would also say is ultimately in real life, I mean, all these gate counting and all we do, these are all approximations to kind of reality. Ultimately, all that matters is how much area of silicon it takes. Okay, and that, of course, you won't know until the chip has been designed. Okay, so it's a little tricky, but upfront, all this gate counting we do are kind of crude estimates. Okay, so let's pick another example. Okay, so what we have is a timer for a laser gun. So this is what it needs to do. So we have to design this controller. It has a clock. It has a signal X which controls the laser gun. It has a signal B coming in, which is coming from a button. And the idea is that whenever we push this button, we want to fire the laser for 3 clock cycles. And if the button is pressed while the laser is already firing, then we need to ignore the button. So the idea is you press the button, the laser fires for 3 clock cycles, then you are supposed to lift, and if you lift the finger before the 3 cycles are up, the laser will keep firing for 3 clock cycles. If you press the button again before the 3 clock cycles are up, it will have no effect. So the button is kind of locked out. So it's a little bit like, so you have to release, wait for the laser to finish firing before you press again if your button has to have an effect. Okay. So again, kind of a contrived example, but you can imagine again these kind of systems you encounter. If any of you watch Jeopardy, perhaps their kind of button answering button is kind of like this, right? If you press it while others have pressed, you are locked out. If you press it repeatedly, you are locked out. So this kind of press the button and you are locked out if you press too early. Behavior is often present. So that's what we have out here. So press the button for 3 clock cycles. If the button pressed while laser is already firing, we ignore it. So as an example, so imagine this is our clock, and my input looks like the following. So button was unpressed, and the button got pressed. At this clock edge, the one corresponding to the dotted line, we will see that the button is pressed. So the laser output, X output, which is controlling the laser, was 0 until this point. Then it goes high at this clock edge, and it will remain high for 3 clock cycles before going down. Okay, so now what is the state I need to remember? So intuitively, what you need to remember out here is how far along am I in my laser firing, right? So one possibility is currently laser is not firing. Another possibility is laser is firing but only for 1 clock cycle. Another possibility is laser is firing but for 2 clock cycles. And final possibility is laser is firing and it has been 3 clock cycles, right? So there are 4 possibilities that one could imagine in terms of relevant history. Nothing else really kind of matters. So the very first thing therefore we do is kind of say, okay, conceptually what are the states? laser not firing, laser firing, 1 cycle has been up, laser firing, 2 cycles have been up, laser firing, 3 cycles have been up. Nothing else really matters because, so we draw those 4 states. Laser is off, laser is on 1, laser is on 2, and laser is on for 3. So we give them some names: off, on 1, on 2, on 3. Again, as we saw, the precise mapping of the states doesn't matter at this stage. Again, we have a mode machine. So the outputs are indicated in the state itself. So if it's off, x is 0. If it is an on 1, x is 1. If it is an on 2, x is 1. If it is an on 3, x is 1. So now the remaining thing is to figure out the transitions. So if I'm in off state and button is pressed, so B is high, I move to on 1. If I'm in on 1 state, I will move to on 2 unconditionally. So it's like we have a star out here. If I'm in on 2, I move to on 3 unconditionally. If I'm in on 3, I move back to off unconditionally. This notation says startup, on startup. So you will often see this kind of notation, which basically says when the system powers up, it starts in the off state. Okay, and then finally, this is saying that if I'm in off state and the button is not pressed, then you stay put there. So that's why we have the B prime or not B out here. So that's our state diagram. And then you have to implement this thing. So again, sort of conceptually, what we are doing is we are taking stock of what all our system looks like. It has 4 states: off, on 1, on 2, on 3. And again, I cannot emphasize enough. This part, which is what the states are, is the one which you should think about carefully, because that's really the heart of the problem. You can end up creating useless states. You may end up creating wrong states if you don't get the correct sense of the problem. And again, the problems we are looking at thus far are relatively simple. You have to do more and more complicated problems. But coming up with the set of states, the most challenging thing. Set of inputs, it would be obvious given the problem. Set of outputs would be obvious given the problem. Initial state, sometime it is given, sometime you will have to make some reasonable choice, some decision. Set of transitions, that's the other hard thing. What are the states and how do you move between the states? What are the conditions that cause you to move in what pattern? So it describes, so the transitions basically describe the next state function. That's the role they are playing. In this example, I have 5 transitions, right? Off to on 1, off, stay put at off, on 1 to on 2, on 2 to on 3, and on 3 back to off. So there are 5 edges. So those are our set of transitions. One thing you notice is that in this example also, some transitions are conditional. They depend upon some condition based on the input. In this case, the condition is very simple: B equal to high or B equal to low. Other transitions, such as these other 3 edges, are unconditional. They basically, next clock tick, you move on. And then finally, we have set of actions. What's the output? And both this example and the previous one, we were dealing with, we decided to do mode machines. So our outputs were just associated with the states. More generally, outputs may be associated with may depend on inputs also, in which case we are going to put them on the edges. Okay, so let's see firstly. Yeah, go ahead.
Professor, what is the describes the next state function?
Well, since these edges are telling me, given the current state and given a particular value of input, what is the next state? So basically, these edges are helping me describe what the next state function is, right? So in our state diagram, it's corresponding. This is the combination part of the combinational logic, which corresponds to the next state logic.
So for this example, it is mealy or more.
Say it again.
It is a mealy or more.
So tell me, is this mealy or more? Huh? It's more, right? Because the outputs are sitting in the state.
You do not take it.
Remember, the output value is a function of the state only, right? So it's independent of the input value. If it's independent of the B, right? So if I'm in off state, it is always 0. So if it was melee, you would see a notation like B prime slash something like this. Okay, so that would have meant melee because so in melee machines the outputs appear on the edges. In more machines, output appear on the states. Okay. Yeah. You have a question?
I know what's a laser.
What's a laser gun? Never been to ultrazone? It's a toy gun, shoot laser.
What's it used for?
What's used for? Yeah, so,
It's toy, right?
yeah, it's a toy thing. So, ultrazone, like you should go there if you have never been. Or just, so you basically play in teams. People wear a kind of a tag, okay, and you point your gun at them, and if you hit them, then their tag kind of makes a noise and light and all, and they get killed. And of course, I'm sure you have probably also read like U.S. Navy now has a warship where they have laser guns as opposed to standard cannons, so they kind of shoot down incoming missiles and all using laser. And also, I believe China and Russia, they all have these laser guns to shoot down satellites from Earth orbit. So that's the future of weaponry. Okay. Any other questions?
Can you explain again that the another input in the off state?
Oh, okay. So in the off, if I'm in the off state and if the button is pressed, I go to on one.
No. I mean there is another single input in the left side of the state.
Oh, this one.
Yeah.
Oh, okay. This is indicating. So whenever you see this kind of dark dot, okay, this kind of a dot, it says on power up. You go to the state. So when the system powers up, it starts out in the off. Okay. It's another way of saying is that on power up, there is going to be some reset signal which will make sure that your flip-flops are such that you should be in the off state. Usually, it is very common that whatever is your power up state, you make it to be all zeros. It's a very common strategy. And the reason being that in many chips and all, the flip-flops are guaranteed to start out in the zero state. Okay, so if you design things like that, then upon power up, you will always be in kind of like the force. Any other questions? So actually, I want someone to help me out now out here. So let's try to do a one-hot coded implementation of it. Okay. So let me create a blank page out here, and we'll kind of go back and forth a little bit. So I have 4 states: off one, on one. So let's create off, on one, on two, and on three. Let's call this guy to be 1, 0, 0, 0. This guy to be 0, 1, 0, 0. This guy to be 0, 0, 1, 0. This guy to be 0, 0, 0, 1. Okay? So one hot coded. Now, how many flip-flops do I need? 4, right? 1 for each state. So I'm going to have 4 flip-flops, and I'm not going to draw the clock, okay, just to save the clutter. This one corresponds to off, this one corresponds to on 1, this one corresponds to on 2, this one corresponds to on 3. Okay, so now first thing we have to do is to make the transition logic work. So let's go back to this diagram. So let's look at on 2. So the flip-flop corresponding to on 2 is this guy. What do you think its input should come from? So when should the system would be in on 2 if currently, and looking at this, you can say the only thing is currently it's an on 1. So we basically are going to have a straight line going from here to here. Okay. What about on 3? Same thing. On 3 will basically come from on 2. Okay. What about on 1? So when am I going to be on 1?
You come from off and when B down.
So 2 conditions, right? Currently I should be in off and B should be high. Right? That's basically what we want, which basically says an AND gate. B is coming from the button. Okay. Finally, what about off? Ignore the power up part for the moment, for now. So when would I be in off state next time around? Huh? If you're coming, so that's one condition, right? If currently I'm in on 3 and then.
If Y is not passed again.
So tell me in terms of states and inputs.
So not B and or on 3.
Not quite.
If you're at off and you don't press B.
Right. So the 2 conditions are, one is I could be in on 3 and the other is I am in off and button is not. Okay. So what this suggests to us is, firstly, I need an OR gate. One input of OR gate has to come from on 3. The other input has to come from an AND gate, which has 2 things. Firstly, I should be in off state. And secondly, button should not be pressed. That means I have an inverter. Okay. So that's what, and I have not kind of done the power up part, power up out here. So that we'll ignore in these examples. Okay. Then what about X? When is X high? So when is the gun to be fired? Looking at this, I should be in on 1 or on 2 or on 3. So on 1, on 2, on 3, any one of them is my X. And that, huh? Pardon me? You can use not off also. Yeah. Okay, so his solution is much better than mine, so let's adopt that. Good. Okay. So, yeah.
So, good question. So, it has to be at off, and in that AND gate, that not be and off. Is that off really necessary?
You know, it might be possible to optimize it, but I'm just trying to literally just follow your state diagram. It will never make sense. Now, let's think about it. Is off is currently being an off essential, right? I mean, that's basically what you're asking. And the answer is, yeah, it is, because otherwise I may be in one of the other states and you may accidentally put it. So in this particular case, you cannot do that optimization, although it may be possible in other examples. Okay. So your first thing that you should do is to kind of don't worry about optimization. Just kind of follow a strategy which is guaranteed to work so that you get at least a design. Then you kind of think about optimization. So again, faced with a problem description, inputs and outputs tend to be obvious usually. What the states are and how do you move among the states is where your design comes in. It usually requires a lot of careful parsing of the problem. You may have realized in the midterm, like fourth problem had a huge description, but the solution was very trivial. This is the wiring one. Okay. Oftentimes you face with this thing, like Description is very complicated, looks very overwhelming, but so very important to kind of parse through it carefully. The solution may actually be very simple. Okay, sometimes it's not, but the reason the specification tends to be overwhelming is because you want to make sure there is no ambiguity, right? Okay, so which is why standards and all are designed with like huge thousands of pages of standards. The reason being that you don't want any ambiguity, otherwise one person's Wi-Fi radio may not work with another one because they interpreted some language kind of slightly differently. Okay, so it's very common practice you encounter that the description is usually a lot more complicated than the actual system tends to be. So pay attention to it. Don't get spooked by just the size of the problem description. Your goal is to figure out what the states are, how am I moving between the states. Rest of the stuff, as you can see, is mechanical. Okay, and once you have the mechanical part learned, nailed down, you can always apply it. And don't aim for funky optimizations. Yeah, you may get some extra credit if you really do something, but not worth the risks. Okay, your goal should be to get a correct result. So let's stop here, and we'll pick this thing up next time.